Hi, my name's Andrew McLaren, and I want to help you get a big picture on rate laws. This is a great video if you're at AP Chem or College Chem. I have some other videos that go into rate laws a little bit more in depth, but this is just like how do you get your bearings? What type of order of reaction are you looking at, essentially? And I found there's two questions that are very helpful for this process, and I'll kind of go through those with a couple different examples in just a second. But we're going to talk about the overall reaction order and the overall shapes and then ask if the data that we're looking at is that linear or nonlinear. And if it's nonlinear, can we look at the half-life and think of it as a consistent thing, or does it kind of change with the concentration or change with the time that we're looking at with the data? So when we're talking about rate laws, there's three main equations that you're going to be looking at, either depending on if it's a zero, first, or second order reaction. And I think of first order reactions kind of like radioactive decay, which most people have seen in middle school, and they kind of know that there's a half-life, and half-life is a consistent thing. So there's different amounts of the stuff being used up in the same period of time, but each time half gets taken is a consistent amount of time. So if you know that, then you kind of know what this data will look like when you're talking about a first order reaction. And it should be nonlinear, but also having this consistent half-life. So I've got like a random half-life of 10 years and some portions here and did a little graph so you can see the general shape. So a first order reaction is not linear when you just plot A, and a second order is also not linear when you just plot A. Zero order would be linear there. So if you're asking if something is linear or not, you're basically saying, is it zero order or is it maybe a first or second order reaction? So that's that first question. And then is the half-life consistent or not is basically asking, is this first order or second order? Because if it has a consistent half-life, then that would be first order. If the half-life seems to change over time, then that's going to be a second order or potentially zero order if you haven't thought about linear or nonlinear beforehand. So that's the main idea of what we're looking at today, and we'll look at some example problems of how this might be kind of useful. We're not doing mechanisms today. I've got another video on that big picture. So we're going to look at three different problems. Two are from the AP chemistry exam, and the third one is one that a student gave me for getting ready for that exam. This is very likely to be the style of questions that you would see on a college test. They might actually be a bit easier, but in any case, you can see in this question, they've given us the rate law, which actually already tells you that this is a first order, just because they've written that there. But it's also important to consider in this data set that you can see that this is getting rid of half of the sample over the same chunk of time. So the rate that this is getting rid of is changing with time. So this would be a nonlinear type of graph if we're looking at A versus T. And then it does look like this has a like consistent half-life. So it has the same amount of time to cut the stuff in half each time. So that would be like how you would think about this being first order from just seeing this data here in this table. This graph is a bit tricky because they're plotting the concentration over time. And that's really what I'm asking about something being linear or nonlinear is just that normal graph, just the A compared to T. All of them should be linear at some point if you were to plot them out with respects to the appropriate formula. So if you were able to plot out something of first order with ln, that will be linear. And if you do second order 1 over a, then that should also be linear. But what the linear nonlinear is really asking about is like just the a to t. So I can clearly see that this is not a linear relationship with the a to t graph right there. So that is clearly not zero order. And so then it's like, okay, well, this is either first order or second order. This one is kind of harder to see the consistent half-life, but you can see that this gets linear when you have the one over the concentration. So that should be for a second order reaction. You could potentially try and graph this out and look at the data. It's just not really worth it for the consistent half-life thing for this particular way of looking at half-life problems. So just be aware that sometimes the linear nonlinear comes into place for when you've got different things in the y-axis, but the way that I think of that question is just like looking at A compared to T. And then this is more of a traditional kind of question that you would see on just like a college test where they're giving you some data and they're like, hey, what's the rate law here? Is it zero, first, or second order? And when I look at this graph, you can kind of look at the slopes by going down like a certain amount here and seeing if that is changing. But I can just look at this and say like, oh, well, it looks like to get from 0 to 600, that would be a better comparison to do than for the 12 to or the 600 to 1200 because that's the same change in t. So this is a change of about 600 seconds. This is a change of about 600 seconds. And I can see that this went down. What is that? Not 40, but 0.41 right there in terms of this concentration. And then it went down, what is that? Around 20, 24, I think. So it's gone down a different amount with the same amount of time for the concentration. So I can just look at that and say this is non-linear. So that means that it's definitely not a zero order. And then what we can see is like, does this have a consistent half-life? And the question is like, well, how long is a half-life? So if we were to think about this question, you can see that it's a half-life is maybe about 900 seconds, just kind of splitting the difference here. But then this looks pretty close to two half-lives when you've got 0.22. And that kind of matches this, but not perfectly. And then if we look at this, you would have like this is like 3 half-lives have happened potentially. And so then it's like, okay, 2400, divide that by 3. I think that this is actually 800 seconds. And then you can confirm that with doing that one more time. Be like, okay, well, that going maybe one or two more times, what would that be at? And so another half-life would be at like 3200. So that kind of puts us at the 0.65 right there, 0.065, which kind of matches what we were talking about in the half-life numbers, where it's like, oh, the 0.065 there. And this problem is, there's a little bit more to it for determining the value of k, but we can say that this looks like to me like this is going to be something with a consistent half-life. So I would say that this is a first order, just because we can see that it is definitely not linear, and it does appear to have a pretty consistent amount of time that it takes to cut the sample in half. So then you can determine the value of k. There's a couple different ways to do that. Probably the easiest way for this one is using the half-life formula, where you've got t1/2 is equal to 0.693 over k. We know what the half-life is. That was 800 seconds. So we can then isolate that and solve for k, and that's not too difficult to do. So we could do that, or you could think through the first order, where you've got the ln of the concentration A at some time, ln A naught, and then you've got the K and T. So there's that one formula right here. Actually, yeah, I think it's a minus KT. But in any case, you could plug in the original value and the value that you're at some time and then solve for K. So you could do that, or you could just use the half-life formula because it's a first order. But you would, if it was potentially a second order, you need to use the 1 over A version of this formula for second orders. So you could do that if this was actually looking more like a second order to get the specific value of K. And then if we're trying to get this concentration, it works out really nicely because 4,000 seconds is 5 half-lives. So at 5 half-lives, that should be around this portion of sample. So it's around like 3% of the sample. So that's kind of like how you would go through thinking through these multiple steps together. And I kind of do them both together. So it's not like really question one, then question two, but it's like you're thinking about both of them simultaneously. So yeah, that's about it. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.